Okay, on page 124, number 54, we have a bit of a tricky problem involving a clown, which will be represented by a red dot. Now, we have a lot of vectors acting on it, so let's look at these vectors that they tell us. Well, some of them they tell us, the other ones we have to assume. The only thing we know about the clown is they tell us that his weight is equal to the 890 newtons. So we know his weight is 800 newtons, and he's pulling up on a rope with a tension, creating a certain tension. We don't know what that tension is, but that same rope is also attached to his legs, so when he pulls down on the rope, it's going to pull him away with the same amount of tension. Now this blue arrow here we have our force of friction, and because the clown is technically standing on the ground, there's also going to be a normal force pushing up. Normal force is the force of the ground pushing up on the clown. So these are all our forces. What they want us to find out is what is the minimum tension he would have to pull to break the force of static friction. So we're actually looking for the static friction force, not just any force. And they tell us that the coefficient of static friction for this particular problem is 0.53. So if we look at the net force in the x, we're going to assume that we're just going to put what's the most we can exert in our tension force that would make, so that our tension and our force of static friction, our max force of static friction, cancel out and gives us 0. So that's how our net force in the x is. If we look at our net forces in the y, our net forces in the y are also going to cancel out because he's not really going to move up or down. He should just be moving to the left or right. So the net forces in the y are the normal force pushing up, the tension force pushing up, and those 890 newtons pushing down. So we have a problem because we have three unknowns and only 2 equations. So we have to see if we can somehow break this down and find a relationship between some of these unknowns. One of the relationships is that we can take the force of friction, and we know that the relationship between that is that times the static coefficient equals the normal force, which means the force of static friction is equal to 0.53 times the normal force. So if we plug this in over here, we get 0.53 times the normal force minus the tension equals 0, which means that 0.53 times the normal force is equal to the tension. So then we take that and we can plug it in here. Because see, we have this was our first equation, this was our second equation, and this was our third equation. We needed 3 equations to solve for 3 variables. So we plug it in, we just simply change the 0.53, we substitute them from here. And now we have one equation with 1 variable, so we can solve. Remember, there's like a 1 here. This is 1 times the normal force. So we get 0 equals 1.53 times the normal force minus 890 newtons is equal to 0. So we solve for normal force, and we find that the normal force ends up being 581.7 newtons is equal to the normal force. Now this can help us find the tension, because then we can take this, plug it in here, and we can solve for the actual tension. So we end up with 0.53 times 581.70 newtons, which gives us the tension. So the tension is equal to 308.3. That was kind of bad. And 8.3 newtons. That means he can exert 308.3 newtons and it won't break the force of static friction. But the moment he exerts more than 308.3, the static friction is going to break and the clown will fall.